First, I want to thank the organizers for the invitation to speak. Today, I want to report some recent progress about the Fourier restriction phenomenon on manifolds. In the Euclidean space, the Fourier restriction problems are about whether we can meaningfully restrict the Fourier transform of a function onto a hypersurface in the frequency space. Here, I'm choosing the hypersurface as the unit sphere. Then the restriction problems can be phrased as the LP to LQ mapping norms of the restriction operator. The Fourier restriction conjecture for the full range of the indices P and Q is still open, and it's probably one of the most fundamental problems in Fourier analysis. However, when Q is equal to 2, the problem is completely solved due to Tomas and Stein in the 1970s. The nice thing in this case is we can use TD star. And more precisely, R star R will map from the Euclidean space to the frequency space. Since we're choosing L2 in the frequency space, we can come back to the Euclidean space with index P prime. And R star R has a kernel which can be explicitly computed as the integral on a sphere. It turns out this kernel is also the kernel for the spectrum measure of the square root of the Laplacian. Therefore, from the spectrum measure for the Laplacian, we can propose the Tomas-Stein restriction estimate on any Riemannian manifold. And in terms of the mapping norm of the spectrum measure, the Tomas-Stein restriction estimate is highly dependent on underlying geometry. For me, the easiest way to understand the spectrum measure is from the spectral projection. If you write out the spectral projection from -infinity to lambda, where lambda is the frequency or energy, and taking the derivative with respect to lambda will give us the spectrum measure. We can begin from the compact case. In this case, the Laplacian has a discrete spectrum, and we can write out the eigenvalues for square root of Laplacian as lambda1, lambda2, and so on. Then the spectral projection will only change when you pass through the eigenvalues. When you take the derivative, the spectral measure will be a direct sum of the dot measures at its lambda1 and lambda2. Therefore, the spectral measure will be unbounded at its eigenvalues and 0 otherwise. So it does not have a nice mapping norm. The Tomas-Stein restriction estimate will fail on compact manifolds. The appropriate replacement is the mapping norm of the spectral cluster. For instance, the spectral cluster with a width of 1. So lambda to lambda plus 1. And this is nothing but the integral of the spectral measure. Therefore, if your spectral measure has nice mapping property, so will the spectral cluster, but not the other way around. As an integral form, the spectral cluster estimate is strictly weaker. And in addition, the spectral cluster will imply the RP estimate of the eigenfunctions on compact manifolds. And interestingly, these estimates are also depending on the underlying geometry, especially the geodesics. But this is a whole different story, and we're going to move back to the non-compact case. The restriction estimate have been verified in various of geometries. The asymptotically Euclidean manifolds, the hyperbolic space, and recently the asymptotically hyperbolic manifolds. All of these require the no closed geodesics for the restriction estimate to hold. On the negative direction, Guillermo Hassel and Sikora made a very interesting observation. If the manifold contains an elliptic and closed geodesic, a typical example will be the closed geodesic on an elliptic cylinder, then the Tomas-Stein restriction estimate has to fail. Here is a quick reasoning. Associated with this closed geodesic, you can find these approximate eigenfunctions. And they are called quasimodes. Since the right side is of order lambda to -infinity, you can make a projection onto lambda to lambda plus epsilon for any small epsilon. And you'll be able to reproduce this quasimode with some small error. Therefore, near lambda, when you take the derivative to recover the spectrum measure, since we can take epsilon as small as you want, the spectrum measure will blow up near lambda. Therefore, the mapping norm will be unbounded and Tomas-Stein restriction estimate fails. So the question arises, can we find the manifolds in the presence of closed geodesics such that the free restriction estimate are still valid? And we know those closed geodesics have to be non-elliptic. And now we're moving to our natural candidates, the hyperbolic manifolds. They're open, they're of constant curvature -1, so they are the quotients of the hyperbolic space. Here I'm using n+1 as the dimension of the hyperbolic space. So n is the dimension of the boundary at infinity. The easiest example is the hyperbolic cylinder. There's one closed geodesic at the west, and this one is hyperbolic and unstable. So if you look at the behavior of nearby geodesics, they will diverge exponentially fast from the original one. The other hyperbolic manifolds can have much more closed geodesics, and the structure can be quite complicated. A very useful parameter for us is the dimension of the limit set, delta here. For the hyperbolic cylinder, delta is equal to 0. As delta increases, the set of the closed geodesics will get larger and more complicated. And in the extreme case, when delta is equal to n, the manifold becomes compact, in which case we know the restriction estimate has to fail. So coming back to the restriction estimate in terms of the spectral measure, a very important object is the resolvent for the Laplacian, delta minus z to -1, where z here is a complex number. So on the complex plane, a resolvent is well defined when the imaginary part is greater than 0, and continuous spectral is on the real line. It turns out that you can meromorphically continue the resolvent to a lower half plane with infinite many of poles coming out. And these poles are called resonances. And they are associated with the resonant states, which are the analog of the eigenfunctions in this open case. And for the spectral measure to have a nice mapping norm, we have to have a gap between the continuous spectrum and the resonances. And this is called the spectral gap. Essentially, see, if you have the resonances to be very close to the continuous spectrum, then these associated resonance states will destroy the mapping norms of the nearby spectral measure, just as the effect of the quasimodes we have seen before. And in the 1980s, Patterson and Sullivan were able to prove such a gap in the case when delta is less than n/2. And this is exactly the case where we prove our restriction estimate. And the main tool is still the Patterson-Sullivan theory. I don't think I have time to go over the proof. A very natural follow-up question is what happens when delta is greater than or equal to n/2. The spectral gap was largely unknown before the recent breakthrough by Dyatlov and his co-workers. They were able to establish the spectral gap in the case of hyperbolic surfaces. So in my notation, n is equal to 1. However, such a spectral gap does not necessarily lead to the spectral measure estimate, the restriction estimate, essentially because the gap estimate is purely L2 based, whereas the restriction requires some LP input. The other problems one can consider is the restriction estimate on manifolds with variable and negative curvature. Or we can also consider the case where Q is not equal to 2 in the restriction estimate. These are all problems we can look into in the future. I think I'm going to stop here, and thank you very much.